So intuitive clustering is an algorithm we've come up with that we think works really well in this area. And again, this kind of shows the difference between kind of confirmatory analytics and the exploratory analytics we do. If you're doing confirmatory analytics clustering, you're really looking for clustering that's going to return you some mathematically optimum or close to optimum result. If you're doing exploratory, that's really irrelevant. Why do you care what's optimum? What you're looking for is what's understandable. And so the aha moment in intuitive clustering was looking at an analyst who was working with a k-means result I created, was going through there and picking out the clusters they really liked, putting those to the side, and running a keyword search that had all the names of those clusters as their taxonomy. I thought, well, that's interesting. It seems like there's certain clusters that they really understand, and those are the valuable ones, and all the others are irrelevant. And so it wasn't the optimum centroid that was really interesting to them, it was the simple description that was helpful. So instead of trying to build the clusters based on centroids, I basically built the clusters based on the interesting words. And so I built a dictionary of all the terms I found in the data, and then used this this equation called cohesion to measure which terms were best. And then I basically used a greedy algorithm to find all the best clusters, and then just run iteration of k-means at the very end to get the actual taxonomy built where each example went to just one of those clusters. And this works beautifully. That's actually the clustering algorithm I used for the jams going forward because it was so simple and it allowed me to really quickly get a sense of what was in the data without having to spend a lot of time on each cluster understanding it. So multiple feature spaces. For this, we use generating words and phrases as kind of our first baseline of features. And then we use user input to improve the generation of those features. This can be annotations, it can be user-supplied dictionaries, it can also be synonym lists, it can be patterns, regular expression patterns that define certain things that are interesting for features. So we really try to throw in all the kinds of features that might be helpful to us. I'll show you an example from Cobra of user-defined features. These are up at the top here. We have include patterns and exclude patterns written as simple Java regular expressions. And we use those to define a set of words on the left-hand side that are indicative of certain issues that the company thinks are important for understanding their reputation to the brand. The divide and conquer, a set of techniques. Intuitive clustering comes up here as well to generate taxonomies. We also generate taxonomies based on keywords. So if the user has a list of terms they think are important, we can add those to the mix as a taxonomy. A time-based taxonomy, often that may take data and divide it into an event that's of interest. What happened before the event? What happened after the event in that continuum? Those three classes are actually often the most interesting. Sentiment analysis, dividing data up in terms of, is this a positive event? Is it a negative event? Is it something where people are saying negative things about your product, or are they being complimentary? Those are two very interesting classes. Iterative taxonomy browsing and editing. So when you create these taxonomies, it's often useful to be able to look at them and change them based on what you see in the data. Don't just accept what clustering gives you. Be able to filter that out and take out the things that are uninteresting or confusing. And to do that, if you're going to edit taxonomies, you need a way to visualize them. Visualization is very important for understanding, for using that visual cortex in the brain to really understand what these taxonomies mean at a deeper level. This visualization is one I find very useful in most of my work. It's a scatter plot. What we do here is we use the centroids of clusters as our axes. So this is the x-axis, the distance between this cluster and that cluster. The y-axis is then the distance to this cluster here. And the basic idea is there's a high-dimensional space, but you can flatten it out to a plane using these 3 points. So 3 points make a plane, no matter how high dimensionality. Then you draw a normal line down to the point where it intersects is the actual place you draw it. It's a simple idea, but it's actually a very powerful way to understand relationships between clusters. And what the eye will tell you is, look at this point here. It's kind of an outlier, And you know it's also kind of between the oral cluster and the taste mass cluster in our food bitter taste taxonomy. So the eye can pick these things out where it's very difficult to find that with simple math. Finally, add connections allows you to take the taxonomies you've generated and find ways to understand what's interesting about them. The co-occurrence table is a popular technique to look at two taxonomies at once. Trending lets you look at time over taxonomies. Dictionary analysis lets you take taxonomies and look at them across all the different text content you have at a deep level. Industry landscapes lets you look at the entire field of an industry, looking at companies across the different taxonomies. And network relationships are a good way to look at connections across many individuals or people in a network of some kind. So landscape analysis, the way we use co-occurrence tables here is take a taxonomy, in this case diseases on the left-hand side, take an industry taxonomy, so these are companies across the top. The individual cells are the patents. How many patents does each company have addressing each of these diseases? This is obviously a drug industry taxonomy. We then color the cells by where there's an interesting co-occurrence. So here we're saying that for Amgen, these 26 patents, it's colored pink because there's some kind of affinity there. So we use a chi-square test to indicate, is this a likely thing to have happen, 24 patents for this company in this disease? Or given the size of the company's portfolio and the size of the disease, is that really very unlikely? So the deeper the color, the red color is the most significant. Pink is kind of significant, but not so much. And yellow is kind of improbable, but not significant. So what you'll notice here visually is something kind of leaps out at you. Genentech has significant areas where no one else has significance. So what they've done, they've kind of developed this patent strategy that says, we'll create patents addressing diseases that none of the other companies are working in. And so when those patents come to fruition as drugs, we'll have this market all to ourselves. We'll corner the market. So that as a drug company, it's something you really want to be aware of, you know, how your competition is really approaching the patent landscape. Yes?
A lot of businesses follow that model. If they are producing a product and they discover someone else has got pulled up a patent on that, they just abandon it because they don't want to get in a legal war with other people.
Exactly, and the drug industry is very competitive that way, and that's really been one of our top customers in the patent analytics field because of that very reason. Tools and techniques, subtraction. So this gets to the point of once you've found that connection, that interesting area of overlap, you want to start looking at some examples that really confirm it. You don't want to just assume there's something going on without actually looking at the actual patents or documents underneath the covers. So most typical sorting is a way to decide what documents are you going to look at. Are you just going to look at random documents in that co-occurrence, or should you look at things that are most like all the others in the set? This will help you really make sure that what you're looking at is representative. Value estimation. If there's certain metrics you can use that indicate value in some way, you can look at the more valuable patents first. Modeling. If there's some way you can model what it means to be a valuable patent, that's really extremely important. And prediction, if you can use prediction to tell you what's going to be valuable in the future, that's extremely valuable. So patent value estimation is a technique we use to kind of model what the lawyers told us was the way they looked at the world. They said that when they're looking at a portfolio and trying to decide what to sell or license, they try to find something that introduced a new buzzword technology, maybe something that introduced a web browser to the world, or something that introduced, voice over IP. If they used that term before any other patent used that term, that's really valuable. So what we did, we basically codified that by looking at all the different words and phrases, up to three words in length that were occurring in the claim section of patents, and figuring out when did it first occur. Was this patent the first time that occurred? Or were there other patents that mentioned it earlier? And if so, how much earlier? So this little bar chart tries to indicate this is like the first usage of this term, this is an early usage, this is not so early, and so on. So you basically get a feel for every single patent, how valuable is it by the new technologies introduced, and then it tells you why it's valuable. What is this technology that was introduced, and what's the big deal? So that a patent engineer going to license it can really give a story about why this patent is important and what it's really patenting. Which, if you've ever read patents, isn't always that easy. Okay, how much are we doing on time? I don't want to.